Welcome to Talkcast and to Chapter 6 of my breakdown of The Fabric of Reality. Chapter 6 is titled Universality and the Limits of Computation. Now, David Deutsch is expert in the topics he writes about in The Beginning of Infinity and in The Fabric of Reality. But if we were to talk wheelhouses, as people sometimes do, the thing that you spend your career, your life pursuing, then this is one of those. David Deutsch has a lot of wheelhouses, but this is certainly one right in the dead center of David Deutsch's professional interests. One of the reasons for David Deutsch's fame among other physicists is because of his contribution to this area of science, which we call computation or computer science. In fact, it really was down to David to bring computer science into science itself. Before that, it was treated as an area of mathematics, of pure mathematics, treated in the abstract. And it was David who explained how and why it should be regarded more as a part of physics. It's a simple idea. Computers are made of matter. Matter obeys the laws of physics. Therefore, what computers can do is bounded by the laws of physics. This particular chapter is one of my favourites in the entire book. It is insight bomb after insight bomb, which means I am going to take my time with passages here, even more so than what I normally would, in order to break them down or emphasise them. But I'm going to begin just by reading the first paragraph on the first page of the book, and then I'm going to skip rather a lot, and I'll explain why in just a moment. But let's get into the reading. And perhaps for those picking it up in this episode, for whatever reason, the last episode was about virtual reality generators. Now, why on earth would one write a book about the fabric of reality, about cosmically significant things, and concentrate on something seemingly as parochial and as quirky as virtual reality? Well, there is an important reason why, and that is because we human beings, our minds, are essentially virtual reality rendering machines. We are minds, and we are connected to the rest of real physical reality via senses, which are creating for us an impression of the environment. It's a virtual reality rendering of whatever real reality happens to be, which we don't have direct access to. So virtual reality, a study of virtual reality, not only gives an insight into the workings of people, but things that can do computations more broadly. And hence, David begins the chapter with, quote, "The heart of a virtual reality generator is its computer, and the question of what environments can be rendered in virtual reality must eventually come down to the question of what computations can be performed. Even today, the repertoire of virtual reality generators is limited as much by their computers as by the image generators. Whenever a new, faster computer with more memory and better image processing hardware is incorporated into a virtual reality generator, the repertoire is enlarged. But will it always be so, or will we eventually encounter full universality, as I have argued we should expect in the case of image generators? In other words, is there a single virtual reality generator, buildable, once and for all, that could be programmed to render any environment that the human mind is capable of experiencing?" End quote. But I'll just pick up a couple of short paragraphs here, which speak about the limitations of computers, the way in which computers must be limited by the laws of physics, a taster, so to speak, of why it is that there are these limitations placed upon computers. David writes, quote, "A computer with an effectively unlimited memory capacity can be envisaged in principle, but a computer with an unlimited speed of computation cannot. A computer of given design will always have a fixed maximum speed, which only design changes can increase." End quote. Now, why is this? Well, because we've got this limitation on imposed by the speed of light. Stuff can't happen faster than the speed of light. And so signals can't be sent faster than the speed of light. At the speed of light, sure, but not faster than the speed of light. So you have this inherent limitation imposed by the laws of physics. Let's just read on a little bit further. Quote, "Therefore, a given virtual reality generator will not be able to perform unlimited amounts of computation per unit time. Will this not limit its repertoire? If an environment is so complex that the computation of what the user should be seeing 1 second from now takes the machine more than 1 second to compute, how can the machine possibly render that environment accurately? To achieve universality, we need a further technological trick. To extend its repertoire as far as is physically possible, a virtual reality generator would have to take control of one further attribute of the user's sensory system, namely the processing speed of the user's brain. If the human brain were like an electronic computer, this would simply be a matter of changing the rate at which its clock emits synchronizing pulses. No doubt the brain's clock will not be so easily controlled, but again, this presents no problem of principle. The brain is a finite physical object, and all its functions are physical processes which in principle can be slowed down or stopped. The ultimate virtual reality generator would have to be capable of doing that. End quote. Now, I'm ending the quotation there because then David goes into the details about how virtual reality generators could be built that could even tinker with your own brain. The mechanics of this is interesting, and it's worthwhile if, of course, I presume that people who are listening to this have access to the book. So it might be well worth your while going to the book and reading the few pages that I'm going to gloss over here. I'm just going to skip over because it's about the technical details of how one might go about in the distant future, in a technologically enlightened future, where we could directly intercept the contents of neurons, let's say, and so give you the experience of whatever is physically possible to experience via that method of directly intervening in the neurons, the action of the neurons. We don't need to go into that. Please explore this part of the chapter. No doubt the vast majority of people listening to this have the book. If you don't, get the book and read the details because they are interesting. But basically, look, the idea is that with an advanced neuroscience, with a cybernetic implant, it's going to be possible to tinker with neurons and hence subjective experience, given the requisite knowledge, knowing how to do that. The laws of physics do not prohibit this from happening, so it must be possible given the right knowledge. So I'm skipping those details. Interesting though they are, I'm glossing over them, because the sum of everything David says is basically encapsulated by what he goes on to say, quote, "For our present purposes, technological obstacles are irrelevant. We are not investigating what sorts of virtual reality generator can be built, or even necessarily what sorts of virtual reality generator will ever be built by human engineers. We are investigating what the laws of physics do and do not allow in the way of virtual reality. The reason why this is important has nothing to do with the prospects for making better virtual reality generators. It is that the relationship between virtual reality and ordinary reality is part of the deep, unexpected structure of the world which this book is about." End quote. That's why I begin this episode in the way that I did. It's not an esoteric, quirky sort of bit of technology, this virtual reality stuff. It provides an insight into how it is that knowledge can be constructed about the world and what our situation is, what our relationship is with the rest of physical reality. David goes on, quote, "By considering various tricks, nerve stimulation, stopping and starting the brain, and so on, we have managed to envisage a physically possible virtual reality generator whose repertoire covers the entire sensory range, is fully interactive, and is not constrained by the speed or memory capacity of its computer. Is there anything outside the repertoire of such a virtual reality generator? Would its repertoire be the set of all logically possible environments? It would not. Even this futuristic machine's repertoire is drastically circumscribed by the mere fact of its being a physical object. It does not even scratch the surface of what is logically possible, as I shall now show." Pausing there, my reflection. What he's going to show, and what he's about to launch into, is the diagonal argument, which if you are a long-time listener to Talkcast, you will have encountered before. The beginning of Infinity also goes through explanations of diagonal arguments. This is a really interesting one, a way of showing how even a machine which can render all environments that can be experienced by a person does not contain in its repertoire all logically possible environments. There are things it can't do, and in fact, the things it can't do vastly outnumber the things that it can do. Even though we've begun this whole exercise by trying to define into existence the machine that can do anything when it comes to virtual reality, it can render any environment. We're about to see that, in fact, the attempt to do that, the attempt to realize that in physical reality is impossible. Why? David explains, quote, "The basic idea of the proof, known as a diagonal argument, predates the idea of virtual reality. It was first used by the 19th century mathematician Georg Cantor to prove that there are infinite quantities greater than the infinity of natural numbers, 1, 2, 3, the integers. The same form of proof is at the heart of the modern theory of computation developed by Alan Turing and others in the 1930s. It was also used by Kurt Gödel in his celebrated incompleteness theorem, of which more in Chapter 10. Each environment in our machine's repertoire is generated by some program for its computer. Imagine the set of all valid programs for this computer. From a physical point of view, each such program specifies a particular set of values for physical variables on the disks or other media that represent the computer's program. We know from quantum theory that all such variables are quantized, and therefore that no matter how the computer works, the set of possible programs is discrete. Each program can therefore be expressed as a finite sequence of symbols in a discrete code or computer language. There are infinitely many such programs, but each one can contain only a finite number of symbols. That is because symbols are physical objects made of matter in recognizable configurations, and one could not manufacture an infinite number of them. As I shall explain in Chapter 10, these intuitively obvious physical requirements that the programs must be quantized and that each of them must consist of a finite number of symbols and can be executed in a sequence of steps are more substantive than they seem. They are the only consequences of the laws of physics that are needed as input for the proof, though they are enough to impose drastic restrictions on the repertoire of any physically possible machine. Other physical laws may impose even more restrictions, but they would not affect the conclusions of this chapter." End quote. Okay, so what we've got here is the setup of the concept that we have this computer, and the computer can run an infinite number of different programs, but it has a repertoire, which means the set of all programs, and the set can be infinite, of course. You can have infinite sets, the lists that are infinitely long, okay? There's no end to them. So there's no end to the number of programs in this set. It's infinite. Now, some people have a lot of difficulty with this concept, that if something is infinite, it might not necessarily contain everything logically possible. But a simple way of understanding this is you just think of the set of all positive numbers, 0, 1, 2, 3, 4, 5, off into infinity. It clearly doesn't contain all the numbers. Okay. Specifically, if you were to say, well, it's only the integers, well, it doesn't contain a half, a third, and so on and so forth. And it doesn't contain the negative numbers. Okay. So there are things that aren't in that set. There are numbers not in that set, even though it's got an infinite number of numbers. Similarly, we're going to get to here this idea that although there's an infinite number of different logically possible environments that can be rendered by this computer as a virtual reality generator, it won't contain everything that is logically possible. It won't contain everything that's logically possible. So that's the setup. David goes on to say, quote, "Now let us imagine this infinite set of possible programs arranged in an infinitely long list and numbered, program 1, program 2, and so on. They could, for instance, be arranged in alphabetical order with respect to the symbols in which they are expressed. Because each program generates an environment, this list can also be regarded as a list of all the environments in the machine's repertoire. We may call them environment 1, environment 2, and so on. It could be that some of the environments are repeated in the list because two different programs might in effect perform the same calculations. But that will not affect the argument. What is important is that each environment in our machine's repertoire should appear at least once in the list." David makes a few more remarks that I'm going to, again, skip over and pick it up where he says, quote, "Let me define a class of logically possible environments which I shall call can't-go-to environments." That's spelt C-A-N-T-G-O-T-U. Can't-go-to environments. Partly in honour of Cantor, Gödel, and Turing, and partly for a reason I shall explain shortly. End quote. Very clever. Clever little name there. Can't-go-to environments and due to Cantor, Gödel, and Turing. Let's keep going. Quote, "They are defined as follows. For the first subjective minute, a can't-go-to environment behaves differently from environment 1, generated by program 1 of our generator. It does not matter how it does behave, so long as it is, to the user, recognisably different from environment 1. During the second minute, it behaves differently from environment 2, though it is now allowed to resemble environment 1 again. During the third minute, it behaves differently from environment 3, and so on. Any environment that satisfies these rules, I shall call a can't-go-to environment. Now, since a can't-go-to environment does not behave exactly like environment 1, it cannot be environment 1. Since it does not behave exactly like environment 2, it cannot be environment 2. Since it is guaranteed sooner or later to behave differently from environment 3, environment 4, and every other environment on the list, it cannot be any of those either. But that list contains all the environments that are generated by every possible program for this machine. It follows that none of the can't-go-to environments are in the machine's repertoire. The can't-go-to environments are environments that we can't go to using this virtual reality generator. End quote. Pausing there. That's the diagonal argument. That's a kind of diagonal argument. It illustrates a couple of things, that this infinitely long list that can of programs that can render any environment at all the environments that are possible, limited only by the memory capacity of the computer, let's say. You've got environment 1 that it can render. Maybe it looks like Earth as it is today. Environment 2, maybe it is Earth as it was yesterday. And repeat for all the days in the past, and then for environments on Mars, and so on and so forth. This infinitely long list of environments that the computer can generate based upon programs in the computer. But the ones that it can't render are infinitely greater in number. There's many, many more. After all, environment 1 is one such environment that can be rendered. Now, all that we require is that our first can't-go-to environment differs from environment 1 in any way, shape or form. But there's an infinite number of ways in which it could differ from environment 1. So already we've got an infinite number of ways it could differ, and then infinite number of ways it could differ from environment 2, and so on and so forth. So the ones that can't be rendered, the can't-go-to environments, vastly outnumber the number of environments that can be rendered, even though the ones that can be rendered are infinite in number. Okay, let's keep going. David writes, quote, "Clearly there are enormously many can't-go-to environments because the definition leaves enormous freedom in choosing how they should behave. The only constraint being that during each minute they should not behave in one particular way. It can be proved that for every environment in the repertoire of a given virtual reality generator, there are infinitely many can't-go-to environments that it cannot render. Nor is there much scope for extending the repertoire by using a range of different virtual reality generators." Okay, no, end quote. I won't go on and read the explanation of that. Leave that as an exercise to the reader. Instead, I'll pick it up where David writes, quote, "Thus our hypothetical project of building the ultimate virtual reality generator, which had been going so well, has suddenly run into a brick wall. Whatever improvements may be made in the distant future, the repertoire of the entire technology of virtual reality will never grow beyond a certain fixed set of environments. Admittedly, this set is infinitely large and very diverse by comparison with human experience prior to virtual reality technology. Nevertheless, it is only an infinitesimal fraction of the set of all logically possible environments. What would it feel like to be in a can't-go-to environment? Although the laws of physics do not permit us to be in one, it is still logically possible, and so it is legitimate to ask what it would feel like. Certainly, it could give us no new sensations because a universal image generator is possible and is assumed to be part of our high-technology virtual reality generator. So a can't-go-to environment would seem mysterious to us only after we had experienced it and reflected on the results. It would go something like this. Suppose you are a virtual reality buff. In the distant, ultra-high technology future, you have become jaded, for it seems to you that you've already tried everything interesting. But then one day a genie appears and claims to be able to transport you to a can't-go-to environment. You are sceptical, but you agree to put the claim to the test. You are whisked away to the environment. After a few experiments, you seem to recognise it. It responds just like one of your favourite environments, which on your home virtual reality system has program number X. However, you keep experimenting, and eventually during the Xth subjective minute of the experience, the environment responds in a way that is markedly different from anything that environment X would do. So you give up the idea that this is environment X. You may then notice that everything that has happened so far is also consistent with another renderable environment, environment Y. But then, during the Yth subjective minute, you are proved wrong again. The characteristic of a can't go to environment is simply this. No matter how often you guess, no matter how complex a program you contemplate as being the one that might be rendering the environment, you will always be proved wrong because no program will render it on your virtual reality generator or on any other. Sooner or later, you will have to bring the test to a close. At that point, you may well decide to concede the genie's claim. That is not to say that you could ever prove that you had been in a can't-go-to environment, for there is always an even more complex program that the genie might have been running, which would match your experiences so far. That is just the general feature of virtual reality that I have already discussed. Namely, that experience cannot prove that one is in a given environment, be it the centre court at Wimbledon or an environment of the can't-go-to type. End quote. So that harks back to previous chapter, talking about not knowing that you are not being able to confirm that you are on an actual rendering of the real Wimbledon, which is to say, you can't confirm, you can only ever disconfirm, logically speaking. Moving on, David writes, quote, "Anyway, there are no such genies and no such environments. So we must conclude that physics does not allow the repertoire of a virtual reality generator to be anywhere near as large as logic alone would allow. How large can it be? Since we cannot hope to render all logically possible environments, let us consider a weaker, but ultimately more interesting, sort of universality. Let us define a universal virtual reality generator as one whose repertoire contains that of every other physically possible virtual reality generator. Can such a machine exist? It can. Thinking about futuristic devices based on computer-controlled nerve stimulation makes this obvious. In fact, almost too obvious. Such a machine could be programmed to have the characteristics of any rival machine. It could calculate how that machine would respond under any given program to any behaviour by the user, and so could render those responses with perfect accuracy from the point of view of a given user, any given user." Pausing there, my reflection, just perfect accuracy there. Remember, that was defined in the previous chapter, and it's basically where the user themselves is unable to distinguish. And if you're unable to distinguish, X from Y, then to you, to a perfect degree of accuracy, X is equal to Y. All right? That's all. It's just the subjective perfect accuracy. It's not perfect accuracy in real life, in sort of on an objective sense, which doesn't exist. Let's keep going. Quote, "I say this is almost too obvious because it contains an important assumption about what the proposed device, and more specifically its computer, could be programmed to do. Given the appropriate program and enough time and storage media, it could calculate the output of any computation performed by any other computer, including the one in the rival virtual reality generator. Thus, the feasibility of a universal virtual reality generator depends on the existence of a universal computer, a single machine that can calculate anything that can be calculated. As I have said, this sort of universality was first studied not by physicists, but by mathematicians. They were trying to make precise the intuitive notion of computing or calculating or proving something in mathematics. They did not take on board the fact that mathematical calculation is a physical process. In particular, as I've explained, it is a virtual reality rendering process. So it is impossible to determine by mathematical reasoning what can or cannot be calculated mathematically. That depends entirely on the laws of physics. But instead of trying to deduce their results from physical laws, mathematicians postulated abstract models of computation and defined calculation and proof in terms of those models. I shall discuss this interesting mistake in Chapter 10. That is how it came about that over a period of a few months in 1936, three mathematicians, Emil Post, Alonzo Church, and most importantly Alan Turing, independently created the first abstract designs for universal computers. Just pausing there, my reflection, I might just go back and just to mention that this argument here, this explanation about the fact that mathematics consists of, well, explanations, but it requires calculations. It uses proofs and computations. And these things are completed by physical systems, whether the mathematician themselves or computers and pocket calculators and that kind of thing. So are bound necessarily by the laws of physics. So what is able to be proved is limited by the set of things that the laws of physics say is provable. Because you're building computers out of matter. The matter obeys laws of physics, and those laws of physics only allow certain kinds of things to be proved. The laws of physics bound what can be mathematically proved. Okay, so many mathematicians don't like that. That doesn't matter, doesn't affect the fact that it's true. Many people don't like that. They think that somehow mathematics has to be prior to physics in some sense. Now, all that said, precisely the same argument applies even more broadly to reasoning in general. Reasoning in general. You can't get outside of the laws of physics. What can be known is bounded by the laws of physics. And so philosophy, epistemology, reasoning itself is done by physical things, human beings, brains, minds, and they obey laws of physics. So it is the laws of physics that constrain the possibility of what we can think, what we can know, what we can reason. This is not a problem as such, but it's just worth keeping in view and understanding. It does come to bear on our capacity to know, but it doesn't come to bear on our capacity to solve problems that we're interested in. In particular, it's the very thing that allows us to know that problems are soluble. Problems are soluble precisely because, well, the physical structure of our brain, what it's able to do uniquely is generate explanations, which can be in one-to-one correspondence with the rest of physical reality. That's what the laws of physics allow. The laws of physics provide constraints, but allow for that, and therefore allow for the solving in principle of any possible problem we could encounter. Problems are soluble. And David's going to get to that, essentially get to that in this chapter. But I think one reason I'm also saying that is that philosophers who are sometimes disconnected to some extent from physics fail to take this into account and think that physics can be irrelevant to what they're doing, but it's not. Not utterly irrelevant. It's not to say that everything reduces to physics. I'm not being reductionist in this sense. Or that the philosopher needs to refer to what's going on in physics now and again. But the reasoning itself, it has to be understood, is itself bounded by what the laws of physics permit us to reason about. And so if you're trying to, the common error here that really, I guess I'm circling is prophecy. That philosophers, epistemologists, others who don't take this on board fully, think that there must be a mechanism, whether by induction or something else, that allows them to forecast the future perfectly accurately. But that is in contravention to laws of physics. It's that kind of thing that, importantly, is constrained by laws of physics. Laws of physics set a bound on what is knowable. And one thing that's not knowable is the creation of knowledge creation. The future cannot be known with perfect fidelity. Also because of laws of physics, as well as the fact that people create explanatory knowledge, which changes the future in ways that cannot be known ahead of time. Okay, that's a major theme of Beginning of Infinity, a theme throughout Topcast as well. So I'll just point to earlier work on that kind of stuff rather than going down the road of making that argument again. But just to say that a knowledge of this kind of physics can help the philosopher and the epistemologist, the people who are interested in knowledge, rather than being utterly disconnected from things. And I think that where some philosophers go wrong, and especially when they fall into pessimism, it can be because of this. Okay, back to the book. We're talking about how Emil Post, Alonzo Church, and Alan Turing, most importantly, created the first abstract designs for universal computers. Okay, so abstract designs, important to know. Not a physical design, abstract, mathematical theory of the computer. without being concerned about the physical laws that actually control these things. David writes on this. Each of them conjectured that his model of computation did indeed correctly formalise the traditional intuitive notion of mathematical computation. Consequently, each of them also conjectured that his model was equivalent to, had the same repertoire as, any other reasonable formalisation of the same intuition. This is now known as the Church-Turing conjecture. Turing's model of computation, and his conception of the nature of the problem he was solving, was the closest to being physical. His abstract computer, the Turing machine, was abstracted from the idea of a paper tape, divided into squares, with one of a finite number of easily distinguishable symbols written on each square. Computation was performed by examining one square at a time, moving the tape backwards or forwards, and erasing or writing one of the symbols according to simple, unambiguous rules. Pausing there, my reflection. This is one of the most jarring insights that goes unsaid, untaught, unlearnt, I think, these days. Unless one takes on pure mathematics course, takes an interest in this kind of thing, goes into computer science, whatever. That no matter how diverse this technology of computers becomes, how ubiquitous it becomes, that all of it can be modelled. Okay, but modulo what David is about to say and the insights that David brings with quantum computation, all that other stuff. But it can be modelled by, reduced to, the action of reading an infinitely, well, not infinite, but, a very long tape divided into squares with symbols written on it. That's what computers do. It doesn't matter how complicated the program. It could be running a word processor. It could be simulating the collision of galaxies. It could be running a computer game. It could be, Facebook or Twitter or a flight simulator. Whatever the program is, whatever the thing is that the computer can do, is based upon code, a program. And that itself can be represented as symbols of zeros and ones on a long strip of paper. Remarkable. Absolutely remarkable. And when you get into the details of this, that how this, in principle, could be done for any program is perhaps jarring to people. That a complicated computer program could reduce to such a simple thing, such a simple idea. And this is the first model of computation, which predated the existence of any actual computer that had been built, okay, any electronic computer. Let's keep going. And David writes, quote, Turing proved that one particular computer of this type, the universal Turing machine, had the combined repertoire of all other Turing machines. He conjectured that this repertoire consisted precisely of every function that would naturally be regarded as computable. He meant computable by mathematicians. But mathematicians are rather untypical physical objects. Why should we assume that rendering them in the act of performing calculations is the ultimate in computational tasks? It turns out that it is not. As I shall explain in Chapter 9, quantum computers can perform computations of which no human mathematician will ever, even in principle, be capable. Pausing there, my reflection. Now, why should there be things that a human mathematician cannot, even in principle, calculate? Does this violate the universality of the human mind? It doesn't. Why? Well, because calculation is not explanation. Now, quantum computers harness something called entanglement and interference phenomena. I go to talkcasts that are about the multiverse to go into that, or to read sections of the Fabric of Reality or the Beginning of Infinity to understand or have more insight into entanglement and interference phenomena. But anyway, quantum computers use this. But this is not how brains, presumably, do what they do. That's not how they do their computations. So although a person cannot calculate what a quantum computer can, a person can't quickly do the prime factorization of a 15-digit number, or calculate the position, let's say, of electrons in some uranium atom. This does not prevent us from understanding those things and what is going on there, and using technology to do it. We can still understand it. We can still explain those things, that phenomena. There is a difference between calculation, which in physics allows, some precise prediction, and understanding the explanation that allows for that prediction to be made. We're still universal. Human beings are people. People are universal, universal explainers, not universal calculators. Indeed, I don't think there can be a universal calculator. After all we need to do is to just think of a number large enough whose prime factorization could never be done, even in the multiverse, no matter how much time you gave it. Just whatever number that is, I don't know, 10 to the power of 10 to the power of 1,000,000 to the power of 7 or something. I don't know. There must be some number out there which it's just so large that the prime factorization would just take longer than the life of the universe. But maybe the universe goes on forever. Maybe if the universe is eternal and this computer lasted forever and had an infinite amount of energy, maybe then you could have this universal calculator. But put aside that, there are non-computable functions, as Turing, in particular Gödel, proved. There are these non-computable things anyway. Okay, let's go back to the book. Quote, "It is implicit in Turing's work that he expected what would naturally be regarded as computable to be also what could, at least in principle, be computed in nature. This expectation is tantamount to a stronger, physical version of the Church-Turing conjecture. The mathematician Roger Penrose has suggested that it should be called the Turing principle. The Turing principle, for abstract computers simulating physical objects. There exists an abstract universal computer whose repertoire includes any computation that any physically possible object can perform." So that's the Turing principle, David goes on to say. Turing believed that the universal computer in question was the universal Turing machine. To take account of the wider repertoire of quantum computers, I have stated the principle in a form that does not specify which particular abstract computer does the job. Pausing there, my reflection. Yes, so this is David's addition to Turing's work, the generalization of what Turing started. Turing's principle, David proved, and which laid the foundations for quantum computation, that there is such a physical object that can be constructed that is able to do the computations of anything, of any computable thing can be computed by this particular thing, and that includes anything made of matter, obeying laws of physics, its behaviour is going to be computable. It goes on to say, quote, "The proof I have given of the existence of can't-go-to environments is essentially due to Turing. As I said, he was not thinking explicitly in terms of virtual reality, but an environment that can be rendered does correspond to a class of mathematical questions whose answers can be calculated. Those questions are computable. The remainder, the questions for which there is no way of calculating the answer, are called non-computable. If a question is non-computable, that does not mean that it has no answer, or that its answer is in any sense ill-defined or ambiguous. On the contrary, it means that it definitely has an answer. It is just that there physically is no way, even in principle, of obtaining that answer, or more precisely, since one could always make a lucky, unverifiable guess, of proving that is the answer. For example, a prime pair is a pair of prime numbers whose difference is 2, such as 3 and 5, or 11 and 13. Mathematicians have tried in vain to answer the question whether there are infinitely many such pairs or only a finite number of them. It is not even known whether this question is computable. Let us suppose that it is not. That is to say that no one and no computer can ever produce a proof either that there are only finitely many prime pairs or that there are infinitely many. Even so, the question does have an answer. One can say with certainty that either there is a highest prime pair or there are infinitely many prime pairs. There's no third possibility. The question remains well defined, even though we may never know the answer. In virtual reality terms, no physically possible virtual reality generator can render an environment in which answers to non-computable questions are provided to the user on demand. Such environments are of the can't-go-to type. And conversely, every can't-go-to environment corresponds to a class of mathematical questions. What would happen next in an environment defined in such and such a way, which it is physically possible to answer? Although non-computable questions are infinitely more numerous than computable ones, they tend to be more esoteric. That is no accident. It is because the parts of mathematics that we tend to consider the least esoteric are those we see reflected in the behaviour of physical objects in familiar situations. In such cases, we can often use those physical objects to answer questions about the corresponding mathematical relationships. For example, we can count on our fingers because the physics of fingers naturally mimics the arithmetic of the whole numbers from 0 to 10. Pausing there, my reflection. Pure mathematics doesn't need to concern itself about whether it applies to physical stuff. The pure mathematicians can consider pure abstractions, okay, the things that aren't made out of material at all and don't obey the laws of physics. Even though what can be known is constrained by the laws of physics, that's a separate issue, quite a separate issue. The constraints placed on mathematics by the laws of physics aren't constraints that prevent mathematics from delving into non-physical stuff. Indeed, pure mathematics is largely about non-physical stuff. There's a great YouTube video of Richard Feynman talking about mathematics and physics, the relationship between them, and the relationship between the mathematicians and the physicists in particular. It's almost like a stand-up routine. That man was just so engaging, so entertaining, and so funny when he talks about certain things. And that particular one, I'll try and remember to provide a link in the description to this video to that one. I can't put a clip here. I'd like to be able to put a clip here, but it seems when I do that, they take down the entire video, and it's such a hassle, so I have to avoid putting clips in these days. But in it, like Feynman's basically saying, your physicist is sort of interested in specific cases. He's not interested in general cases. He goes along to the mathematician and he says, I'm interested in, like the laws of gravity, for example, in three-dimensional space. I just need for three-dimensional space. And the pure mathematician will say, well, for an n-dimensional space, here are the theorems that follow. And the physicist will say, I'm not interested in n dimensions. I'm not interested in just the arbitrary, sort of force. I'm not interested in arbitrary spaces of n dimensions. I'm interested in a specific case. And the pure mathematician will say, well, just substitute n equals 3 then. And then, of course, Feynman goes on to say something like, then, of course, the physicist has to go crawling back to the pure mathematician at some point and say, you're talking about those n-dimensional spaces. What about the case of n equals 4? No, because sometimes the general case turns out to be very useful for the physicist. And there is this cross-pollination that happens between physics and mathematics, of course. What is done in pure mathematics sometimes is thought to be utterly irrelevant. And, I've mentioned before the case of G.H. Hardy and A Mathematician's Apology. He wrote this book about, meeting Ramanujan, another famous mathematician. And Hardy said of his own work that he didn't think it would ever have any applications to anything ever. And he was quite proud of it. He regarded it as more being like art. Okay, it's exploring the space of mathematics for its own sake. But in fact, his own work, I think, it went on to be used in electrical engineering, and it had applications anyway. It had proper applications later on, and that's the unpredictability of the growth of knowledge. And it can happen in the other direction as well. Physicists can do work in physics, which then goes on to have a bearing on what happens in mathematics. I think things like chaos theory. There's first investigated by physicists about how seemingly purely deterministic systems, obeying simple laws, can actually become chaotic. Now, even if you assume that the classical laws of physics, the perfectly deterministic laws of physics, they can lead to these extremely complex behaviour. A double pendulum is one such thing, which has this interestingly chaotic behaviour. So that comes from physics and goes into pure mathematics, and the pure mathematicians can explore that kind of thing. But yes, if you want to laugh, definitely look up Feynman talking about mathematics and physics. Let's keep going. David writes, quote, "The repertoires of the three very different abstract computers defined by Turing, Church, and Post were soon proved to be identical. So have the repertoires of all abstract models of mathematical computation that have since been proposed. This is deemed to lend support to the Church-Turing conjecture and to the universality of the universal Turing machine. However, the computing power of abstract machines has no bearing on what is computable in reality." Pausing there, my reflection. Yes, so here, this is the genius of David Deutsch. This is where it comes in, right? I mean, if you regard Turing as a genius for the insight about all of this computation stuff, which he certainly was, then so is this insight by David, okay? It may seem simple in retrospect, like so much of science just seems simple, like, well, why couldn't I think of that? Well, because you're not thinking about this particular problem all the time. You could, any of us could, but we didn't. It's the people that are passionately curious and interested in these particular problems and push the frontier of science, in this case, physics and computation, forward. This whole idea that thinking about computation as actually being physical and not merely an abstract thing, it takes insight, questioning assumptions. And that can be hard. Which assumptions do you question? And once you question those assumptions, what do you replace them with? What's better? It's no point just saying, oh, let's assume that's false. Well, then what are you going to put in its place? If nothing, does it lead to something better or not? Even recognizing, noticing in the first place that something is an assumption at all is hard. Computation is assumed to be abstract and not physical? Oh, is it? Yeah, that's an assumption. And I guess a lot of the mathematicians who were doing this didn't realize the assumptions they were making. Who notices that kind of thing? What is the consequence of that? It's like, physics is about dynamical laws. You plug in the initial conditions and you calculate what goes on next. But that's an assumption as well. What if we relaxed that assumption and considered something deeper about what is possible and impossible? Why would we ever question the very foundations of physics? Who would ever do that? Well, these things take creative leaps, don't they? And those creative leaps can be the hard part. You have to sit down and you have to be creative and you have to think about these things. They're hard and yet not hard. They're hard in once someone's done it, you can look back and you go, how could it have been otherwise? It's that kind of thing. But it's beforehand, before the creative act has taken place that, people are struggling to make the progress. And yet it always seems in retrospect, that was so simple. I could have done that. Yeah, you could have. But you weren't focused on that problem, were you? And yet this is the kind of thing that anyone interested in progress needs to strive for. It's not to say, well, you just go around assuming everything is false and then you're done, question everything and then you're done. No. You need an alternative. This is the hard part. You need to, take what is known now, regarded as the best explanation now, figure out what could possibly be false about it, and replace that with something better. Something that is going to have consequences that you can investigate and pursue, or that others can, perhaps. And then you might have a whole new field of physics, let's say. You might have a whole field of quantum computation, say. Okay, let's keep going. David writes, quote, "The scope of virtual reality and its wider implications for the comprehensibility of nature and other aspects of the fabric of reality depends on whether the relevant computers are physically realizable. In particular, any genuine universal computer must itself be physically realizable. This leads to a stronger version of the Turing principle." The Turing principle for physical computers simulating each other. "It is possible to build a universal computer, a machine that can be programmed to perform any computation that any other physical object can perform. It follows that if a universal image generator were controlled by a universal computer, the resulting machine would be a universal virtual reality generator. In other words, the following principle also holds. The Turing principle for virtual reality generators rendering each other. It is possible to build a virtual reality generator whose repertoire includes that of every other physically possible virtual reality generator. Now, any environment can be rendered by a virtual reality generator of some sort. For instance, one could always regard a copy of that very environment as a virtual reality generator with perhaps a very small repertoire. So it also follows from this version of the Turing principle that any physically possible environment can be rendered by the universal virtual reality generator. Hence, to express the very strong self-similarity that exists in the structure of reality, embracing not only computations, but all physical processes, the Turing principle can be stated in this all-embracing form. The Turing principle. It is possible to build a virtual reality generator whose repertoire includes every physically possible environment. This is the strongest form of the Turing principle. It not only tells us that various parts of reality can resemble one another, it tells us that a single physical object, buildable once and for all, apart from maintenance and a supply of additional memory when needed, can perform with unlimited accuracy the task of describing or mimicking any other part of the multiverse. This set of all behaviours and responses, that one object exactly mirrors the set of all behaviours and responses of all other physically possible objects and processes. The set of all behaviours and responses of that one object exactly mirrors the set of all behaviours and responses of all other physically possible objects and processes. Pausing there, my reflection. So this is the basis of quantum computation. This says that you can build this thing, this computer, quantum computer, which, so long as you have the program, so long as you know what to feed into this computer, it can represent that environment. It can represent that world. In particular, if you have a theory of physics, then you can program it in, you can model the rest of physical reality. And it also implies the existence of people who can understand, because they also are rendering these environments with their models of science, that this can be done too. That this is the comprehensibility of physical reality as well. Well, it allows for the comprehensibility of physical reality as well. Let's go on. David writes. On this exact point, David goes on to write, quote, "This is just the sort of self-similarity that is necessary if, according to the hope I expressed in Chapter 1, the fabric of reality is to be truly unified and comprehensible. If the laws of physics as they apply to any physical object or process are to be comprehensible, they must be capable of being embodied in another physical object, the knower." Pausing there, my reflection. So that's the universal explainer. Now, this particular passage is where I say David's just dropping insight bombs. It's just so much of the beginning of infinity yet to come. Even stuff of the science of Canon Kant, the constructor theory. And it's just deep, deep stuff. So I'll go on, okay? And then I'm going to go back and I'm going to read some of this again for emphasis. It's important. David writes, quote, "It is also necessary that processes capable of creating such knowledge be physically possible. Such processes are called science. Science depends on experimental testing, which means physically rendering a law's predictions and comparing it with a rendering of reality." End quote. So we've moved from the existence of the universal computer, the Turing principle, to the idea that knowers are able to come to an understanding of physical reality that's entailed within this. And also that science, therefore, is possible, and physically testing theories is possible. This is all coming from the same thing. Now, I apologise if anyone feels patronised that I'm just belabouring the point, but it's just for anyone who's new to this, these can be deep insights. And it's one reason why, because of the density of consequences that flow from, and David pursues these consequences, but the density of them, the number of them, the depth of them, means that sometimes the worldview is difficult to convey in, let's say, a few tweets. That it's all built, in a sense, as a web of these interconnected explanations about reality, which have these connections between physics, mathematics, epistemology, science, more broadly, philosophy. Let's keep going. David writes, "It also depends on explanation, and that requires abstract laws themselves, not merely their predictive content, to be capable of being rendered in virtual reality." End quote. So there we have David in the fabric of reality. Again, laying out the deep themes of the beginning of infinity. And again, the idea of the knower here, okay, and the purpose of science. Abstract laws themselves being explained, not merely being about their predictive content, being able to predict stuff. Instrumentalism is false. David goes on, quote, "This is a tall order, but reality does meet it. That is to say, the laws of physics meet it. The laws of physics, by conforming to the Turing principle, make it physically possible for those same laws to become known to physical objects. Thus, the laws of physics may be said to mandate their own comprehensibility." End quote. So it's that kind of passage that sets the book apart from other books. It is not merely the science, it's philosophical exploration of these ideas, and hence provides a whole worldview, a way of thinking about reality that is coherent as far as we can tell. It's the deepest one that we can tell, providing for cosmic significance of people and comprehensibility of that cosmos. And it goes on with more insight bombs, but really I just have to, without interruption, go back and just read through that, okay? Because David's talking about self-similarity. What is this self-similarity? Self-similarity is, well, and I talk about this in my Nexus video. The idea here is that in a person's mind, they represent the rest of physical reality. There's a self-similarity. There's relationships between ideas you have in your mind that correspond to some degree of accuracy with physical reality. That's what self-similarity is. And so that connection between us and the cosmos, or all of reality rather, every single thing that can be known, makes us unique and important. So let's just go through and read that again, because it is just one of the reasons why this is one of my favorite chapters. It's the wheelhouse of David Deutsch. It underscores the worldview presented to us in both of his books hitherto. This optimistic, all-encompassing way in which these findings, like the Turing principle, allow for comprehensibility, infinite progress, solving of problems. Let's just read it again. And enjoy it without my interruption. Quote, "This is just the sort of self-similarity that is necessary if, according to the hope I expressed in Chapter 1, the fabric of reality is to be truly unified and comprehensible. If the laws of physics as they apply to any physical object or process are to be comprehensible, they must be capable of being embodied in another physical object, the knower. It is also necessary that processes capable of creating such knowledge be physically possible. Such processes are called science. Science depends on experimental testing, which means physically rendering a law's predictions and comparing it with a rendering of reality. It also depends on explanation, and that requires the abstract laws themselves, not merely their predictive content, to be capable of being rendered in virtual reality. This is a tall order, but reality does meet it. That is to say, the laws of physics meet it. The laws of physics, by conforming to the Turing principle, make it physically possible for those same laws to become known to physical objects. Thus, the laws of physics may be said to mandate their own comprehensibility." Amazing stuff. The scientific view of the deep importance of human beings as people. The scientific view. The rejection of parochialism and the principle of mediocrity, and pessimism about people as a chemical scum. That's all there. That we are unique and, in some sense, written into the laws of physics. Okay, let's keep going. David writes, quote, "Since building a universal virtual reality generator is physically possible, it must actually be built in some universes. A caveat is necessary here. As I explained in Chapter 3, we can normally define a physically possible process as one that actually occurs somewhere in the multiverse. But strictly speaking, a universal virtual reality generator is a limiting case that requires arbitrarily large resources to operate. So what we mean by saying that it is physically possible is that virtual reality generators with repertoires arbitrarily close to the set of all physically possible environments exist in the multiverse. Similarly, since the laws of physics are capable of being rendered, they are rendered somewhere. Thus it follows from the Turing principle in the strong form for which I have argued that the laws of physics do not merely mandate their own comprehensibility in some abstract sense, comprehensibility by abstract scientists as it were, they imply the physical existence, somewhere in the multiverse, of entities that understand them arbitrarily well. I shall discuss this implication further in later chapters. Pausing there, just my reflection. Yes, so when it says there, just be aware. Now, I'm not speaking, this is me talking, this is not David talking. I could be wrong. Mistakes my own. This could be one of them that I'm about to make. But my understanding of that there is when he says they imply the physical existence somewhere in the multiverse of entities that understand them arbitrarily well, he's not saying that here right now, at the same time as us, somewhere there are aliens that exist that understand them arbitrarily well. It's that we could be those entities. If we're not, then someone else will be. Some other species will be. But we could be that species. We could be those entities that understand the physical laws arbitrarily well. In other words, people are mandated by the laws of physics. If they're possible, they exist somewhere. Well, here we are. Here we are. Now, it could be the case that a great catastrophe wipes us out. That the Bostroms and Reeses and various other intellectuals who think that civilization could come to an end. We all think it could come to an end, but they tend to be putting their eggs into that basket of civilization crumbling. They could be right. And if they are right, then we won't be the ones that go on to understand the physical laws arbitrarily well. But other people will. Okay? So that's my understanding of that we could be the ones. I think we will be. It appears to be the case. There needs to be a history of optimism written that things are getting better. Not irrevocably, not necessarily, but there are explanations that go into allowing for the dynamic society which we are occupying right now. And the robustness and the resilience of this society is growing, not diminishing. Of course, hyperbole and pessimism is increasing to some extent in some places, but optimism is increasing in other places as well. Okay, so in the West, sometimes we end up having a bit of a blinkered view because our intellectuals have a certain culture at the moment. I think it's transient. I think that there'll be a resurgence of optimism. People are going to get bored. They're going to get bored with the constant pessimism. The constant way in which human beings talk down human beings and talk up the environment. This can't last. This can't last. I'm hopeful. Okay, let's keep going. I don't want to get too off track. David writes, quote, "Now I return to the question I posed in the previous chapter. Namely, whether if we only had a virtual reality rendering based on the wrong laws of physics to learn from, we should expect to learn the wrong laws. The first thing to stress is that we do have only virtual reality based on the wrong laws to learn from. As I've said, all our external experiences are of virtual reality, generated by our own brains. And since our concepts and theories, whether inborn or learned, are never perfect, all our renderings are indeed inaccurate. That is to say, they give us the experience of an environment that is significantly different from the environment that we are really in. Mirages and other optical illusions are examples of this. Another is that we experience the Earth to be at rest beneath our feet, despite its rapid and complex motion in reality. Another is that we experience a single universe and a single instance of our own conscious selves at a time, while in reality there are many. But these inaccurate and misleading experiences provide no argument against scientific reasoning. On the contrary, such deficiencies are its very starting point." Pausing there, my reflection. Yes, so this is the refutation of empiricism. Our senses don't provide us with accurate information. We need science. Science is about explaining what we see in terms of what we don't see. It's the seen in terms of the unseen. My desk here, made of wood, solid, continuous matter. It feels nice and smooth. We know it's bumpy atoms. Can't see the atoms. My senses are not going to be able to tell me that. But we have theories, and we had theories of atoms before we had scanning electron microscopes that could produce images for us of those atoms. No image is possible. No way of seeing what is going on in the core of the sun. The core of the sun is not directly observable. We can see the surface, but we know what's going on there. We know what's going on there because of our explanations. Big Bang, no one's going to be there to observe it. No one was there to observe it, but we know what happened. No one's going to see a dinosaur. Almost everything in science is like this. We don't see the stuff that really explains what we do see, whether because it's too small, too vast, too far back in time, so on and so forth. Science is about the seen in terms of the unseen. We get an inaccurate experience of reality. Our experience is virtual reality. Real reality, okay, we can come to approximate that more and more over time, more and more closely over time. And we do. But still, we're just barely scratching the surface, as the beginning of infinity emphasizes. They're always at the beginning of infinity. We're always just scratching the surface. Our virtual reality rendering, understanding, improves over time. That's science. That's that kind of virtual reality. And then there's the virtual reality of us just being minds running on brains. In the darkness of our skulls, that's where we really are. But we are connected to the rest of physical reality via these imperfect sense-gathering things, eyes and ears and hands and so on. Okay, let's keep going. David writes, quote, "We are embarked upon solving problems about physical reality. If it turns out that all this time we have merely been studying the programming of a cosmic planetarium, then that would merely mean that we have been studying a smaller portion of reality than we thought. So what? Such things have happened many times in the history of science, as our horizons have expanded beyond the Earth to include the solar system, our galaxy, other galaxies, clusters of galaxies, and so on, and of course, parallel universes. Another such broadening may happen tomorrow. Indeed, it may happen according to any one of an infinity of possible theories, or it may never happen. Logically, we must concede to solipsism and related doctrines that the reality we are learning about might be an unrepresentative portion of a larger, inaccessible or incomprehensible structure. But the general refutation I have given of such doctrines shows that it is irrational to build upon that possibility. Following Occam, we shall entertain such theories when and only when they provide better explanations than simple rival theories." Pausing there, my reflection. Yeah, exactly. Realism, allows for progress to be made, problems to be solved. But the opposite, solipsism, well, how do you build on that? What follows? Okay, it's all a dream. Okay, what follows? If what follows, Jaron Lanier makes this problem, if what follows is, well, science still works in the same way it would under realism, you've just got an unnecessary assumption, don't you? Realism is just works, but let's add on top of that, but it's all a dream. Why not just do away with the, but it's all a dream, but it's all a simulation, and just get on with science, because that's the most parsimonious way of working. Assume things are real. David goes on to write, quote, "However, there is a question we can still ask. Suppose that someone were imprisoned in a small, unrepresentative portion of our own reality, for instance, inside a universal virtual reality generator that was programmed with the wrong laws of physics. What could such prisoners learn about our external reality? At first sight, it seems impossible that they could discover anything at all about it. It may seem that the most they could discover would be the laws of operation, i.e., the program of the computer that operated their prison. But that is not so. Again, we must bear in mind that if the prisoners are scientists, they will be seeking explanations as well as predictions. In other words, they will not be content with merely knowing the program that operates their prison. They will want to explain the origin and attributes of the various entities, including themselves, that they observe in the reality they inhabit. But in most virtual reality environments, no such explanation exists, for the rendered objects do not originate there, but have been designed in the external reality. Suppose that you are playing a virtual reality video game. For the sake of simplicity, suppose that the game is essentially chess. A first-person perspective version, perhaps, in which you adopt the persona of the king. You will use the normal methods of science to discover this environment's laws of physics and their emergent consequences. You will learn that checkmate and stalemate are physically possible events, i.e., possible under your best understanding of how the environment works. But that a position with 9 white pawns is not physically possible. Once you had understood the laws sufficiently well, you would notice that the chessboard is too simple an object to have, for instance, thoughts, and consequently, that your own thought processes cannot be governed by the laws of chess alone. Similarly, You could tell that during any number of games of chess, the pieces can never evolve into self-reproducing configurations, and if life cannot evolve on the chessboard, far less can intelligence evolve. Therefore, you would also infer that your own thought processes could not have originated in the universe in which you found yourself. So even if you had lived within the rendered environment all your life and did not have your own memories of the outside world to account for as well, your knowledge would not be confined to that environment. You would know that even though the universe seemed to have a certain layout and obey certain laws, there must be a wider universe outside it obeying different laws of physics, and you could even guess some of the ways in which those wider laws would have to be different from the chessboard laws. Arthur C. Clarke once remarked that any sufficiently advanced technology is indistinguishable from magic. This is true, but slightly misleading. It is stated from the point of view of a pre-scientific thinker, which is the wrong way around. The fact is that to anyone who understands what virtual reality is, even genuine magic would be indistinguishable from technology, for there is no room for magic in a comprehensible reality. Anything that seems incomprehensible is regarded by science merely as evidence there is something we have not yet understood, be it a conjuring trick, advanced technology, or a new law of physics. Pausing there, that seems like a tweetable quote, doesn't it? I'll read it again. Anything that seems incomprehensible is regarded by science merely as evidence that there is something we have not yet understood, be it a conjuring trick, advanced technology, or a new law of physics. And he goes on to say, reasoning from the premise of one's own existence is called anthropic reasoning. Although it has some applicability in cosmology, it usually has to be supplemented by substantive assumptions about the nature of oneself before it yields definite conclusions. But anthropic reasoning is not the only way in which the inmates of our hypothetical virtual reality prison could gain knowledge of an outside world. Any of their evolving explanations of their narrow world could, at the drop of a hat, reach into an outside reality. For instance, the very rules of chess contain what a thoughtful player may realise is fossil evidence of those rules having had an evolutionary history. There are exceptional moves such as castling and capturing en passant, which increase the complexity of the rules but improve the game. In explaining that complexity, one justifiably concludes that the rules of chess were not always as they are now. In the Popperian scheme of things, explanations always lead to new problems, which in turn require further explanations. If the prisoners fail, after a while, to improve upon their existing explanations, they may of course give up, perhaps falsely concluding that there are no explanations available. But if they do not give up, they'll be thinking about those aspects of their environment that seem inadequately explained. Thus, if the high-technology jailers wanted to be confident that their rendered environment would forever fool their prisoners into thinking there is no outside world, they would have their work cut out for them. The longer they wanted the illusion to last, the more ingenious the program would have to be. It is not enough that the inmates be prevented from observing the outside. The rendered environment would also have to be such that no explanations of anything inside would ever require one to postulate an outside. The environment, in other words, would have to be self-contained as regards explanations. But I doubt that any part of reality, short of the whole thing, has that property. End quote. End of the chapter. Long one today, but as I hope you will agree, this just is so dense and deep and sort of has feelers into the rest of the book and into the beginning of infinity and the worldview, as I say. This way of understanding the place of human beings and people in the cosmic scheme of things, how it is that we can go about creating an infinite stream of solutions to the problems that we encounter via creating knowledge. And there's the bounds imposed by the laws of physics are there and they're real, but they don't prevent us from making infinite progress, which is what optimism is all about. But because this has been a long one, I won't have a long outro today. And instead I'll just say, until next time, bye-bye. Of course, if you would like to support this endeavour of me exploring the worldview, that is contained within the philosophy of Karl Popper, the science and philosophy of David Deutsch, constructor theory, infinite progress, rational optimism, so on and so forth. All the good stuff that we talk about here, then please go to my website, www.bretthall.org, and there are links to Patreon and PayPal. Until next time, bye-bye.